Hello, welcome back to this post-lunch session of today's event. I am Debraj Das, the chair for this session. We have 5 talks in total, and we will start with Professor T.S. Mahesh from IISER Pune, and he is going to speak about propelling quantum states, recent NMR experiments.
Thank you, Debraj. Let me thank Abhishek for inviting me. It's a nice, pleasant experience to be here every time. I enjoy ICTS the most. Good afternoon, everyone. It's very difficult to sit through the first lecture after lunch. I try to make it a little bit entertaining. So let's see. The idea is how we can propel quantum state from one initial state to another final target state as quickly as possible. And we know the obvious reason. So we want to fight against decoherence. So the idea is like we have a quantum state, and we want to propel it as fast as possible to the target state, and we apply a drive. And so I will talk about adiabatic drive because we want to reach a particular target state. And so we use one of the possible ways is to use adiabatic drive. But we can't go very fast, we know. So in this case, there is a drag, atmospheric drag. So we put a fairing. So in the analogous way, for the drive, in the case of adiabatic evolution, we can put additional correction that is called counter-diabatic drive. So that allows us to go faster, okay? So without causing transitions, without causing unwanted transitions, diabatic evolutions. So, but that is not enough sometimes. It is not the best way to do adiabatically. So one can think of other methods. One of the methods that we recently worked on is QAOA, quantum alternating operator ansatz. So that has multiple stages. So you switch between two Hamiltonians. So it is alternating operator ansatz. And that allows you to go much faster. And Michel is my student, he's here. He's going to give a detailed talk on the last day of this conference. So I'll be talking very briefly how we can do this QAOA. And one can also do a little bit better. So this is a recent method. Morning we heard about feedback in the case of open quantum systems. We can also do feedback in the closed quantum system. Of course, this can be extended to open quantum system also. So that takes some part from the output and gives it back, and so that makes it very, very efficient and very, very robust. So that's the method Falcon. I'll talk about Falcon. And after all these things, one can use additional things. So this was described by Arijit, very beautiful talk on Wednesday. So what he talked about was using an ancilla to propel the quantum state very fast. So that's an superposition of unitary operators with the help of ancilla. So that's similar to in this picture, that is gravity assist. Okay, so that's the idea. So we want to propel the quantum states as quickly as possible. Okay, coming back to the architecture that we are going to use. Okay, sorry, this is scrolling. Good. Okay, so first let me describe nuclear magnetic resonance. So that's the architecture I'm going to use. So as Rangit has already given a very beautiful introduction to NMR, I don't have to describe. This is just one slide description of what is going on. We have a diamagnetic sample, so we don't have to think about electrons. So there is no net electron spin angular momentum. So there is only nuclear spin angular momentum. So we have molecules. Inside the molecules, we have atoms, and atoms have nuclei, and they have nuclear spin, and they are our qubits. So if you take a spin half nuclear spin, so it's a 2-level system, we assign 0 state to 0 label to ground state and one label to excited state, so that is our bit, and it's a quantum bit. And so it's in some thermal bath, and there is some population distribution. And there is energy gap, and this energy gap, if it matches with the external irradiation that is provided in the form of radio waves, if there is resonance, then there is a resonant transitions. And we can control the resonant transitions very precisely. We can prepare superposition states very accurately, very precisely. That is one of the strongest points in nuclear magnetic resonance. We can prepare the coherences very precisely, and also they live pretty long. I'll talk about the lifetimes. So, they also give out radiation, and that radiation is picked up by these Helmholtz coils. And that is sent for processing, and that comes out as NMR signal. Okay, so that's the one slide description of nuclear magnetic resonance. And this is our NMR lab. Okay, so using that nuclear magnetic resonance, we can do NMR spectroscopy. We can use it as a test bed for quantum computing. In fact, the initial experiments on quantum computing were mainly done by NMR spectroscopy, including the first demonstration of factoring by Shor's algorithm. We can develop quantum control methods, which will be useful for other architectures. It will be useful for any other quantum technologies. Just like Rangit described how he can develop methods for ion trap and other methods. So we can simulate quantum evolutions. We can do various types of quantum simulations. We can study quantum transport, many body effects. And we can also use NMR to study quantum foundations. Okay, so I'll briefly talk about one of these. Okay, so that's various things. This is just the physics part of it. Of course, NMR has many other applications beyond physics. It can be used, it is essential bread and butter for chemists. It is very, very important in medicine. For example, MRI is nothing but NMR, and so on. NMR has various applications. Now, when I talk about the qubits, so we talk about the collection of qubits, that is registers. So we can take various molecules, and depending on how many accessible and useful spins we have, that forms the number of qubits. We can have 12 qubits like this, or we can have 18 qubits, or even recently we have shown 38 qubits, depending on different degrees of control we have. Or in the case of solid state NMR, where we have global control, we don't have local addressability. If we want to just study some bulk phenomena like decoherence and so on, this is very useful in solid state NMR, and people have gone to about 5,000 qubits and study their decoherence properties. And this is very important to develop tools for decoherence suppression. Okay, so with that introduction, let me go to the first part of the talk. So the idea is to take some initial state, some convenient initial state, and go to a target state. I'll talk about the target state in a while. Now, what's the method? So so here, the first method I'm going to talk about is using adiabatic state preparation. So you choose two Hamiltonians. So that is initial Hamiltonian and the final Hamiltonian. That target state is the ground state of the final Hamiltonian. Okay. And the idea is you start with the ground state of the initial Hamiltonian, and you interpolate the Hamiltonian from initial Hamiltonian to final Hamiltonian using a scalar parameter lambda. And if lambda is 0, you are in the initial Hamiltonian. If lambda is 1, you are in the final Hamiltonian. And if you do slowly, adiabatically with this condition, then so you will be transferring the ground state of the initial Hamiltonian slowly and accurately to the ground state of the final Hamiltonian. So that's the standard adiabatic evolution, adiabatic state protocol, state preparation protocol, and it's very popular. But the problem is this: to maintain this adiabatic condition, it has to go through very slow evolution, and then the system is no longer closed. This is based on this entire calculation is based on the closed quantum system. And so there will be decoherence, and it will not go to that state, it will go to some other mixed state. So that's the problem. So This problem has different solutions, and one interesting solution is to add a counter-diabetic term. And so this was proposed in the last decade, and there are many, many works. So I will not be citing all of them. This is one of them. So the idea is you have this interpolated Hamiltonian, you put on additional term, and you calculate this additional term such that there is no transitions. So the transitions are suppressed. And this you can calculate. You can put this back to Schrodinger equation and solve the entire time-dependent evolution and find what should be the form of this additional term. And you can get to first order. It is of this form, okay, to the first order. And then you can find what should be the solution. And so you can get some kind of this. And the first order term is proportional to the commutator between initial Hamiltonian and the final Hamiltonian. So this is a very small correction that you are going to introduce to the interpolated adiabatic term. Now, so that is the counter-diabatic evolution. So this is a correction to the interpolation Hamiltonian in order to suppress the transitions. So that allows you to go much faster. So now I'm going to take the specific example. So we have a target state now. So the target state that we are going to take is long-lived singlet state, and this is a very important state in NMR. So basically it's an eigenstate of this Hamiltonian minus I1 dot I2 or sigma 1 dot sigma 2. And this is just a Bell state, singlet state. But why it is long-lived? It has zero angular momentum, and it is non-magnetic and immune to collective noise. And all these things we already know. And prominent decoherence causing mechanisms in NMR are dipole interactions, and that is symmetry preserving, and it cannot convert singlet state into triplet states. And that's the main reason why this state can live much, much longer than other non-equilibrium states. In fact, it can far outlive the T1 relaxation time. In fact, it can live as long as 30 times T1, and it can, so in terms of absolute times, it can sustain for minutes, even hours. So that has tremendous applications in spectroscopy, MRI, quantum information processing. We have shown some applications in quantum computing, and it has opened a new branch in NMR since 2004. So this singlet state preparation is very important. And so what we need is an efficient, robust, and general protocol to prepare such long-lived singlet state from thermal states. Okay, so now what we can do now, so that's the target state, singlet state. So we have thermal state, and so this is the initial Hamiltonian, of which we can prepare the ground state easily, and this is the final Hamiltonian, that is minus I1 dot I2, so of which singlet is the ground state, and we add the counter-diabatic term, and this was calculated by Michel, and Michel is here. If you have questions, I'll forward it to Michel. So these are the solutions of this, and so it has the lambda term, so that's the interpolation parameter that has to be chosen carefully, as well as there is this coefficient of this counter-diabatic term, and that is also should be calculated carefully depending on the Hamiltonian parameters, and J is the coupling between the two spins. Now, if you do that, and then it can be quickly decomposed into NMR pulse sequence, what you find is the following. If you find the energy levels, so this was the original energy level evolution for the interpolated Hamiltonian, and with the CD correction, you can see that energy levels are pulling apart. Okay. Now, since the energy levels are pulling apart here, so you can go faster. So that allows you to drive the state faster, okay, without causing transitions. Okay. So that's the idea. And how well it works. So this is one simple example. This is one particular system with two spins, and we start with a thermal magnetization, and we want to prepare singlet state, and this is adiabatic signal. After a long time, we get this signal. This is the characteristic signal of the long-lived singlet state, and we can get same singlet state with much shorter time. And you can see the this is a fidelity versus total duration. You can see for same duration, this is adiabatic and this is counter-diabatic, and you can see that fidelity is much, much better in the case of counter-diabatic evolution. Okay, so that's about adding counter-diabatic evolution. And so in general, it is also advantageous to use not just one interpolated Hamiltonian, but to use something more general. And so that was proposed recently. So this is not the first paper on QAOA. This is one review. It has very nicely described all aspects of quantum alternating operator ansatz. So what you do is, instead of relying on one interpolated Hamiltonian, you switch Hamiltonian between two conveniently implementable Hamiltonian. You can choose any two conveniently implementable Hamiltonians that don't commute. So you alternate between these two Hamiltonians, which are experimentally easy and robust, and then until you get the desired state. Now, how do you compute these two Hamiltonians and how long you apply, what strength you have to apply? Vishal will give a detailed talk on 6th February. Okay, so this is just the, again, the same target state. It is the important long-lived singlet state. And we can apply, this is the NMR pulse sequence. So you can ignore about these two parts, Vishal will explain later. So these are the switching Hamiltonians. So we have one Hamiltonian, another Hamiltonian, and you alternate between these two for P1 times. In our case, just 3 times, if you switch between these two, we get beautiful singlet state. So that is the power of this QAOA. And now what we are interested in is we apply noise deliberately. So this is the way to apply noise in NMR. So we apply pulse field gradient. Basically, you create a field, magnetic field inhomogeneity and use the molecular diffusion in the liquids to simulate the noise. Okay. So if you do that, and then you can see what is the advantage of a QAOA sequence. So initially, in the presence of no noise or low noise, so you see that the green is adiabatic sequence, that works better. But in the presence of noise, you see that QAOA is much better. So that is orange. Okay. So it is more robust, the sequence is more robust against noise. Okay, so that's QAOA. So now we have put multiple stages. Okay, so now the next one is Falcon. So this is feedback-assisted, feedback-based algorithm for quantum optimization. This was described by these people in 2022. So the idea is that you may want to go from some state to some target state. You may not know everything about the initial state. It may be completely unknown state or it may be partially known state. But you still want to go to target state. What do you do? So that's the idea. So here you don't need to know the initial state completely. And what you need to do is intermittently you have to measure certain observable, and based on that measured expectation value, you decide the control. And this is a very nice method because it tells you to go to the target state while you are blindfolded, because you don't know anything about the initial state, but all you need to do is measure expectation values at certain intervals. Okay, so let me give one example. So we have, let's say we have a quantum battery. Okay, so quantum battery is a battery which operates on quantum principles. So it can spin half. You can say it's a quantum battery because if you say it's in the ground state, it is completely discharged because it has no energy. If it is excited state, it has some energy which can be taken away, right? So it's a completely filled battery. Okay, so now we have such a battery, and then the goal is to discharge the battery. Okay, so we have some charge state. We don't know what is the exact charge state of the quantum battery, and we want to discharge it. We want to extract work from it. Okay. So what we can do is, so the idea is to take unknown state to ground state. So that's the idea. What we can do is, so we assume a set of conveniently implementable drives. Okay, I'll describe what is that. So it can be like a sigma X drive or sigma Y drive, and so some interaction drive and so on. And with the tunable strengths. So I have control on how much I can tune sigma X, how much I can tune sigma Y, and so on. Okay, so now you write down the Schrodinger equation, and now find, we have to find the drive strengths because our drives are fixed, but we just need to know the strengths of the drives that minimize the energy. And from this, you can get a Lyapunov condition, which should follow this condition. But now what should be the drive here? So if you take this beta, the drive, which is exactly this, then you can see that this whole thing is a real number. This is also a real number. So product should be a positive, and there is a negative sign here. So E dot is always negative. That means energy always goes down. Okay. So in order to find this beta, the drive strength, you just have to measure this expectation value. But this expectation value looks strange because it has a commutator. You may be wondering it is very difficult to implement. But there is a very easy method to do that. What you do is you exponentiate it. You get a unitary operator because it's Hermitian. You get a unitary operator and you apply controlled unitary, and then you apply the controlled unitary with respect to some ancilla prepared in plus state, and you measure the sigma y expectation value of the ancilla, and that exactly gives you some signal proportional to that. So all you have to do is take an ancilla and apply this controlled operation, and the signal sigma y expectation value is proportional to this. So now with the help of an ancilla, you get to know what should be the drive strength for the next iteration. So you have an unknown state, you find out, apply this unitary using an ancilla and measure this signal, and then find out what should be the drive. And you do this in an iterative way, and you can discharge the battery. Okay. So you can take it to ground state. Even unknown quantum state can be taken to ground state. So that's the power of this method. Okay, so let me just introduce one interesting concept. So I'm sure many of you know this. So this is called ergotropy. This was introduced in the year 2004. So here the idea is to quantify what is the maximum work unitary extractable from a arbitrary state rho naught of a system governed by H naught. So you have a quantum system in rho naught, and what's the maximum energy you can extract unitarily. So you can't apply non-unitary operations, only unitary operations, and what's the maximum energy you can extract, and that's ergotropy. Now, after the maximum work is extracted, the system ends up in a state from which you can no longer extract further energy using unitary means, and that's called passive state. Now, the difference between the initial state, energy of the initial state, and the passive energy, and that is called ergotropy. Okay. So that just quantifies the maximum extractable energy unitarily. Okay, so now it has been proved by these people that if H naught and rho naught in their respective eigenbases, if you can write down, then passive state is of this form. It is diagonal in the energy basis. So passive state is always diagonal in the energy basis. That's the best you can do. So you can take any superposition state, mixed state, or pure state, whatever it may be, and the passive state is always of this form. Okay, it has been proved. Where this the populations are always decreasing, because if it is increasing, you can still get energy by downward transitions. But populations are always of this form. It is decreasing population with increasing energy. So that's what it says. So with increasing energy, decreasing population. So in the case of single block sphere, so whatever may be the initial state, the state that is on the circle on the upper hemisphere on the diagonal, so on the 0, 1 diagonal, so that is the passive state. So you can rotate to this, and that's a passive state. So that has the minimum energy. You can't take it to that because that requires non-unitary operation. You can only go from here to here and then stop it. That's passive state. So that's a single qubit. Okay, so now you have an unknown state, how to take it to passive state and how to measure that ergotropy. What was the energy that can be extracted? So we used again the Falcon method that I described. We call this method as FQ ergo. So you prepare some random states and then apply the iterations. You measure the commutator, expectation value of the commutator, and use that as drive. And so in this case, we used only sigma x drive. And after 10 iterations, the energy saturates, and that is the passive state. You can't go any further. So that's how it goes. So you start from arbitrary state, it always ends up in the 0, 1 diagonal state. These are the experiments. But now it gets more interesting in the case of 2 qubits. So what happens in the 2 qubits is, so now you can prepare states of different degrees of entanglement. So this is the entanglement entropy. So this is 0 means it is separable, 1 means it is fully entangled, and in between we can prepare states with different degrees of entanglement. Now what happens if you start with only local operators, the energy starts saturating. So it doesn't decrease further because using local operations, you cannot convert entangled state into separable states. So energy cannot be extracted. If it is fully entangled, local operations cannot extract energy. Moment you switch to global operations, so that means interaction between the spins, you can extract energy and it goes down and it reaches passive state. Now the difference between the locally extractable energy and the globally extractable energy is called ergotropy gap. And we have shown that ergotropy gap is an entanglement witness. So this now gives another way to estimate entanglement, at least witness entanglement, because you don't need tomography, you don't need anything, you just have to measure energy and you can find out whether there was entanglement or not. So ergotropy gap is a measure of entanglement, is an entanglement witness. Okay, so now you can test this on different degrees of entanglement. Every time you see that there can be some part of energy which can be extracted locally and some part only globally. So the difference is the ergotropy gap. And so it's just a passing comment that charging a quantum battery sounds easier than discharging because you may not know what is the initial state of the quantum battery. So discharging a quantum battery is not trivial, especially when you have multi-qubit or multi-dimensional quantum battery. Because energy can be hidden in some correlated space and you don't know which drive to use to extract the energy. Okay, so that's about Falcon. So now coming to the last part. So this Arijit has already described very beautifully other day on Wednesday. So let me go a little bit quickly. So this is the Ancilla assisted propulsion. The motivation came from one experiment we had done, one of the motivations, one experiment we had done a few years ago. This is called delayed choice experiment, quantum delayed choice experiment. The idea is like this: you have a Mach-Zehnder interferometer with 2 beam splitter, so BS1 and BS2. So in this case, BS2 is missing. So if you have a photon arriving at this beam splitter, it can go in the blue path or it can take the red path, and it can go to these 2 detectors. If it takes 0, then 0 path, it can go to D0 detector. If it takes 1 path, it goes to D1 detector. And irrespective of phi, this is a phase difference between these 2, D0 and D1 get clicks. There is no dependence on the phi phase at all. Okay? Because there is only 1 beam splitter, there is no beam splitter here. You don't see interference pattern. Since you don't see interference pattern in this setup, it is referred to as a particle interferometer or particle setup. That is a particle setup of Mach-Zehnder interferometer. On the other hand, if you put a beam splitter here, then you will see that as a function of phi, you see beautiful interference pattern. So that's the interference pattern you see here. So in the top setup, you see like that. So here you see beautiful interference pattern because these 2 paths interfere again by the second beam splitter, and you get interference pattern with respect to phi. Now what you can do is, okay, so then there were many stories about this, like Wheeler had a thought experiment of introducing this second beam splitter after the photon has entered the first beam splitter in order to confuse the photon. Okay, so whether to behave like particle or whether to behave like wave. So that is Wheeler's thought experiment. So he suggested that make the decision of having or not having the second beam splitter after the photon entered the first beam splitter. And he said that it's a test for quantum mechanics because if it disturbs the Bohr statistics, then quantum mechanics must be re-looked into. Anyway, so that experiment was is no longer thought experiment. In fact, French scientists have done that exact experiments. So they have found a way to introduce this beam splitter after the photon has entered the first beam splitter. But in 2011, Australian scientists said there is another way to do this. So instead of making that Wheeler's way of introducing or not introducing decision, you can put the second beam splitter in a quantum superposition of being there and being not there. So that makes it quantum Mach-Zehnder interferometer. And he said, if you do that, then depending on the so you can do that in this way. So you can take an ancilla qubit, and each beam splitter is like a Hadamard operator. The first Hadamard operator is always there, but the second Hadamard operator is controlled by an ancilla. And if this ancilla is in, if you apply pi/2 pulse, it is in one state and it is controlled Hadamard. So then if the ancilla is 0, it is not there. If it is 1, it is there. If ancilla is in superposition of 0 and 1, so that is a quantum superposition of beam splitter being there and being not there. So that's the idea. But now you can apply different degrees of superposition. Instead of taking only 0 plus 1, you can weight it more towards 0 or more towards 1, and you can weigh the particle nature or wave nature continuously. The photon can behave like completely particle or different degrees of particle nature and wave nature until it becomes completely wave nature. So that was the motivation. And using that motivation, so we can generalize a bit. Instead of taking Hadamard operator, we can apply any rotation, U0 or U1, depending on the states of the ancilla. So that now if the ancilla is in superposition, we get superposition of unitaries. The effect is like superposition of unitaries. Right? Instead of superposition of beam splitter, you have superposition of quantum gates. And if you do that, so Arijit has shown other day that it has very interesting speed of quantum evolution. So this is the net evolution that that is experienced by the qubit. And so the qubit will have the speed of evolution, which is like this. So it can go slowly sometimes and very fast sometimes. So that was the analogy I was taking from gravity assist. So you can control the speed of quantum evolution by using an ancillary qubit, just like they enhance the speed of a spacecraft using ancillary objects like planets. Okay, so that works very well. So you can prepare superposition states and of the ancilla, and you can control the speed of quantum evolution, and you can use it to study Leggett-Gerg inequality, and it can beat Serelson bound, and it can hit the algebraic limit. Okay, so I'm almost done. So the interesting part of this experiment is that when we did this experiment, Leggett-Gerg experiment in 2011, we just did normal 3 measurement experiments and found this K3 string, and we found a transition from quantum to classical. And so from 0 to about 165 milliseconds, it was LGI violating, so it is considered as quantum regime of the qubit. And beyond that, it was LGI satisfied. In Leggett-Gerg sense, it is no longer resourceful. There is no Leggett-Gerg resource. But here, in the case of quantum superposition of states, if you can take it to much longer because now speed of evolution is much higher, so it can pass the equator where there is maximum decoherence much faster, and it can escape from being dephased, and it can keep the quantum resource much faster in this sense. Okay, so that's the summary. So I talked about NMR, I talked about adiabatic evolution with counter-diabatic drive. I talked about QAOA and Falcon and ancilla-assisted propulsion. Thank you.
Okay, so questions. Okay, so we have here. Do we have a mic nearby? Okay, so
Thanks for the talk. I have a question about your passing comment about the quantum batteries. You're saying they're easier to discharge than to charge. Is that because you assume them on the charging process? It's unitary either direction. If you do this on an arbitrary state, it looks the same, right?
Correct. Right.
Are you assuming that the
I am
charging
assuming
process...
that charging is from completely discharged state.
From a passive state, so that's local, that doesn't have any correlation, whereas the discharging state is in generally... Okay, that's entangled. Good.
Yes, please.
Hi, Mahesh, nice work. So about this, the first work, I mean, basically the counter diabetic approach. So there, I mean, you have any connection with the quantum speed limit?
Oh yeah, this is a question I expected. I don't know whether people have looked into it. That's an interesting question actually. How you can reach quantum speed limit using optimal CD counter diabetic drive? I don't know whether there is any work on that. But it's an interesting question, yes.
Okay, so there exists some kind of bound on like how fast you can go from
finding exact counter diabetic drive is difficult because that requires spectral knowledge about it at all the time steps which you don't know, because so it's a inverse problem actually. It's a circular problem, but this first order is easy. First order approximation. So I think it will not meet the quantum speed limit because it's already first order approximation. You said something? Yeah.
So this is regarding the Falcon. I mean, basically, it was a time-dependent drive that you discretized. Basically, the amplitude was time-dependent, right? Yeah.
So amplitude in Falcon is fixed, but each interval it is fixed, but the next interval it changes. So like this. So for first interval it is beta 1, right. And then that's randomly chosen, the first one. And then you measure this beta k, and then so that like beta 2, you feed it, and then get beta 3, feed it, and like that. So it is segment dependent.
I understand. I understand. Oh, okay.
Yeah, hi Mahesh. Thank you for the talk. So just a quick question. I'm to be honest, I don't follow the Leggettgard literature, so I'm left very confused. So there is the 1.5, and then there is also the 3.
Yeah.
And yesterday in Urbashi's talk, it kind of seemed that the point was that you could never cross 1.4. Maybe I kind of mistook that.
Yeah.
So there seems to be some imaginary line at 1.5 which you have clearly crossed. So could you?
So there is a Cedric bound.
Yes.
So that is the thing. So you can beat that Cedric bound because we have a unitary which is not divisible. So it is like u of T1 to T2 cannot be divided into or T1 to T3 cannot be divided in general to T1 to T2 and T2 to T3. It is a non-divisible unitary operator. Arijit, you have better explanation for it. You can. So Arijit is an maybe I can take his help to answer. That is one thing. So you are going. It's bit generalized unitary. It is not the unitary that is assumed by Cedric.
So you're saying that because the unitary itself is not a composable map, it's
yes.
a Markovian in some way
it's artificial. It is engineered.
Isn't in general all time-ordered unitary will have this issue that it is not you couldn't just throw it away. But maybe I can just ask Arijit afterwards. Yeah.
Maybe you can discuss with Sai. Okay. So please thank Professor Mahesh.
Is it audible?
Yes.
Yeah, okay. Hi, everyone. First of all, thanks to the organizers for the nice conference. It's a pleasure to be here. My name is Shishir Khandelwal. I'm at Lund University. I'm a postdoc in the group of Armin Tavakoli. So today I'll be talking about some simple but surprising results that we had last year on generating maximal entanglement in autonomous quantum thermal machines. So first of all, what are autonomous quantum thermal machines? They're just setups that utilize incoherent interactions of thermal reservoirs with the system to produce some useful output. So this output can be work, cooling, thermoelectricity. It could also be something entirely non-classical, such as quantum entanglement. So what makes these machines autonomous for me is the lack of external control and time-independent interactions, also lack of source of coherence while the machine is operating. So to me, there are three main reasons to investigate such systems. First of all, in the lack of external classical control, you can aim to explore what is truly quantum in a quantum thermal machine. Secondly, because the machine operates only with the thermodynamic exchange from thermal reservoirs, you can quantify the resources needed for its operation in terms of heat and energy exchange with the reservoirs. And thirdly, and this is a practical reason, so thermodynamic cost of classical control is typically very high, which means that we would typically like to avoid it. For more details, I would recommend looking at this nice review. So let me now come to the problem at hand. So I have here, the problem is you're given an arbitrary quantum state, or more specifically a separable quantum state, and you would like to generate a steady state that is entangled using only thermal interactions and in an autonomous way. So this is a question that, at least to my knowledge, people have considered for about 20 years now. The answer is already known. It's indeed possible to create entanglement in such setups. But there are many recent questions that people have tried to answer. For example, how much entanglement can you generate in such scenarios? Secondly, can you generate entanglement beyond bipartite systems and also beyond qubit systems? For example, these two works. And lastly, and importantly, is the generated entanglement actually useful for anything? So does it have an operational non-classical meaning to it? So let me now give you a very simple but informative example of an entanglement machine. So here I have two qubits coupled to two thermal reservoirs. Here I'm taking fermionic reservoirs. The Hamiltonian of the system is given by this simple expression. And I'm assuming weak coupling between the system and reservoir, and also weak coupling between the qubits. And in this situation, you can express the dynamics of the system in this local Lindblad form, in which these dissipation terms enter locally with the qubits. So here, the dissipators are the usual Lindblad form, and the rates are determined by the statistics of the reservoir. And it is indeed known that steady-state entanglement is possible, in fact, for a wide range of parameters, for example, in this work from 10 years ago. And it's also known that there's a minimum current that you require in the steady state to see entanglement. So this is an if and only if condition, where this is C represents here the concurrence. So it really is the thermodynamic exchange with the reservoirs that drives entanglement production in this scenario. But the problem with this model is that the generated entanglement is typically very weak. It's too weak to be useful for anything. So naturally, people have considered many different ideas for minimal resources that you can add to the setup, both autonomous and non-autonomous, to boost entanglement production. So for example, I said that it's thermodynamic exchange that drives entanglement production. You can imagine that population inversion on one of the reservoirs can give you more entanglement. Also, for example, repulsive interaction, which eliminates doubly occupied subspace, it can boost entanglement even further. And there are also non-autonomous means such as feedback mechanisms and heralding, which may, which are not only autonomous, but in the case of heralding, also non-deterministic. Even though none of these examples are, and many, many others don't go beyond a certain level of entanglement, not close to maximal entanglement, it's known that you can have operational non-classicality in this setup. But what people have not really answered is how much entanglement can you create in the steady state? Can you specifically create maximal entanglement? So to answer this question, it's whether you can create a pure and maximally entangled state in the steady state, it's useful to go back to some basics. So first of all, note that Lindbladian evolution is usually has a mixing effect, which means that if I have an initially pure state and it undergoes some Lindbladian evolution, it will evolve into a mixed state. But exceptionally, if a pure state has to be the steady state of our Lindbladian, it can be shown that there are only two conditions that need to be satisfied. First of all, that the dissipators of the Lindblad equation must annihilate this pure state. And secondly, the state must be an eigenstate of the Hamiltonian. And the proof of this can be found in this paper from 2008. So first of all, note that the Hamiltonian that I showed you for the two-qubit system has two Bell states as eigenstates. So all one has to do is construct a set of dissipators that annihilates this one of these states. And it can be shown, and you can convince yourself with a short calculation that this is the only set of dissipators in the local picture, so in the computational basis, that has this property of annihilating, of being annihilated by these dissipators. The problem now is that this equation does not have a unique steady state. It has 2 zero eigenvalues. So what we've shown is that the two-qubit setup actually cannot produce a unique steady Bell state. So this motivated us to look at the minimal extension to this two-qubit model. So the natural thing is to add one extra qubit. So here I have a 3-qubit system. The first one is coupled to a reservoir at non-zero chemical potential. The second one is decoupled from any thermal reservoir. And the third one is coupled to a reservoir at 0 chemical potential. In addition, you'll see that I have flip-flop interactions between qubits 1 and 3 and qubits 2 and 3, while all 3 qubits are also interacting via some repulsion, Coulomb-like repulsion term. Here I take the ideal limit. So I take a very large Coulomb repulsion, a very large chemical potential, while maintaining that the Coulomb repulsion is much larger than the chemical potential. This may seem rather manufactured and unrealistic, but this is the mathematical condition that we need to reach the state exactly. Actually, the scheme works very well beyond it as well. So first of all, a large Coulomb repulsion will ensure that double occupation does not happen in the state. And a large chemical potential ensures that that this reservoir can only provide excitations to the system. It can never gain anything from the system. This also means that the right reservoir will only be will be the only exit way for excitations from this 3-qubit setup. And the last condition is basically just needed to ensure that there is no double excitation at any point and under any circumstances in the evolution of the system. So beyond this, this ideal limit, you can take arbitrary couplings and arbitrary system reservoir couplings as well, and arbitrary temperatures, as long as you remain within the validity of this Lindblad equation. So without getting into too much detail, most of which you can find in this nice paper from 2021, you will find that when you apply this ideal limit, only 3 dissipators matter. These 3 in particular. And now that we have our Lindblad equation, we can find its steady state. It happens to be given by this expression. And with a simple parametrization of theta, you can see that this is just a partially entangled state of 2 qubits along with the ground state of the 3rd qubit. So what we find is that for any parameter regime of the couplings, the steady state is pure and partially entangled, as long as you are in the ideal limit. This, as expected, and as I said before, this has to be an eigenstate of the Hamiltonian, which is what we find. And lastly, when you take these couplings G23 and G13 to be equal, you find that you have a perfect singlet steady state. So what we find now is that what was impossible with the 2-qubit setup, a third qubit has actually allowed the generation of maximal entanglement in the setup. And this is despite the fact that the third qubit is not entangled at all. It's just always pushed into the ground state. So one can understand this, this result further by taking some inspiration from atomic physics. So let's say I start in the ground state of 3 qubits. So one possibility is that I gain an excitation from this reservoir and go to the state 100. The other possibility is that I gain an excitation from this reservoir and go to the state 001. These two states are now coupled with this interqubit interaction. And there's a third state that is coupled through this interqubit interaction. And in the end, what we're finding is a coherent superposition of these two states. And for those of you with an atomic physics background, you will see a connection with lambda systems here. And what we're finding is that there's a direct analogy with coherent population trapping. For those of you who don't know this, you should look up dark states on Wikipedia, and you'll find this expression. So in the end, what we found is that what this is actually is the solution of the Schrödinger equation of the effective 3-state model when you disregard dissipation entirely. And because this qubit is always depopulated, this means that in the steady state, it can provide no excitations to the right reservoir. And this means that there cannot be any current, despite the fact that the reservoirs are heavily out of equilibrium. So this is what is known as dark or a non-conducting steady state. So now that we have, how much time do I have? Okay, I have time, right? So now that we have a clear picture of how to create maximal entanglement in 2 qubits, we can ask the question whether we can produce genuine multipartite entanglement. So let me remind you, we saw in a previous talk, this genuine multipartite entanglement basically means that the state cannot be written in this biseparable decomposition. It's already known that it's possible to generate GME in such setups, but there are 3 important problems. First of all, you need a heralding procedure, which means that you need to perform local filtering measurements and then post-select on the outcomes. This post-selection also means that this result is non-deterministic. Even though you can produce a large amount of entanglement, there's a near 0 probability of reaching the target state, which is maximal entanglement. And lastly, and very importantly, you need global interactions, which means that they're not just slightly harder to handle theoretically, they're also much harder to create experimentally. So now we ask the conceptual question, are local pairwise interactions sufficient to generate GME deterministically, so with probability 1? So for this, we can make a naive attempt, just adding another qubit to be entangled in our setup. But this actually does not lead to a GME. This does not lead to a unique steady state at all. But instead, if you add another one of these qubits another one of these sync qubits coupled to a reservoir 0 chemical potential, you will find that, basically an extra triangle of interactions here, you will find that qubits 1, 2, and 3 are entangled, while these 2 blue ones are pushed into their ground state. And in the end, we will find, if these couplings are equal, that we have a W state of 3 qubits and ground state of 2 of these blue qubits. And now we can push it further. We can have an n qubit generalization. So we have this machine that creates an entanglement between 3 qubits. We can just make a bigger setup. And for every additional qubit that we want to entangle, we add another one of these sync qubits coupled to a reservoir 0 chemical potential, another one of these triangles. And what we'll find is that we have entanglement between qubits 1 to n. And for each additional qubit that we want to entangle, we again have one extra sync qubit. So the total number of qubits is 2n minus 1. And apart from this, we can have arbitrary system reservoir couplings and temperatures within the validity of the Lindblad equation. And we will find that we have a W state of n qubits. And again, this I'm not going into too much details, but if we take unequal interqubit couplings, we will obtain partially entangled W-like states here. So with this, I would like to conclude. So the smaller, we've shown that the smallest thermal machine that can generate a Bell state as the steady state of its evolution consists of 3 qubits. We also answered the very nice conceptual question whether thermal resources and pairwise interactions can generate the strongest forms of multipartite entanglement. And something that we didn't really talk about is G at Z states. So I had Coulomb interaction in my setup, which will definitely not be useful for generating G at Z states. We also didn't talk about high dimensional entanglement. And I also didn't talk about non-autonomous means of producing entanglement. Since there's a lot of interest at this conference in non-Hermitian physics, I would like to say that there is in fact a way to produce Bell states with some non-Hermitian effects. For more details, I would refer you to this paper. Thank you very much. I'm happy to take any questions.
Thanks, Shishi, for the nice talk. Do you have a question for Shishi? Yes.
This is from a practical point of view. How do you realize sinks in experiments?
So I don't know what the general idea would be, but I've been told by experimentalists in quantum dots that they do it, because the sink idea is actually quite simple. It doesn't have to be zero chemical potential per se. What you have to have is a very large chemical potential on one of the reservoirs. As long as you have this, you don't actually care about what happens here. It can be arbitrary temperature. It can also be non-zero chemical potential, as long as it's not too large.
So you don't really need a bias of temperatures to do this, right?
No, you don't.
Okay. So another thing, can you once more explain that you said something about even if you have bias of temperatures, you don't have currents or something?
Yeah, exactly. So let me go back. So the idea is basically this: because this qubit is depopulated, it cannot transfer any excitations here.
So which 2 qubits are getting, the singlet is between which 2 qubits?
It's between the gray ones, I should have mentioned.
Okay.
It's 1 and 2.
Okay, thank you.
While number 3 is depopulated.
Okay, thank you.
Yeah, hi Shishir. So can you just walk us through again the physics of the limit that you took in the U over G going to infinity?
Sure.
And could you also comment what happens if you just back off of that limit?
Yeah, I can show you a plot if you want, but I can repeat myself with this limit. So the idea is basically this: when you have a large chemical potential here, you're just creating a reservoir that can only provide excitations into your system. It can, if you just calculate the rates with fermionic statistics here, it's easy to see. This thing is necessary to ensure that you prevent double occupation, because in the end you want a singlet state. So you don't want double occupation in the setup. And the last one is slightly more technical. It kind of arises when you look at the rates exactly, and it turns out that it's necessary.
So if you go to kind of spin qubit architectures right now, I guess you could take mu to as large a number as you, I mean, you could design this, but could you spin polarize the leads instead? Like, is that a possible solution out of your T going, like, essentially if you spin polarize the leads by, that's one way to kind of only make sure that electrons flow one way by using Pauli exclusion.
I suppose suppose that could be a way. We never really looked at spin polarization or actually spin qubits. We looked at quantum dots mostly. And in quantum dots, it's just that you have to provide a bias voltage here at this.
Yeah, but if you look at the occupancy with like some finite U models, it's the same. It's just you have to also, poly will allow you to double occupy the states, right? That's what you're trying to avoid anyway. So is this, I mean, and what, so you said that there's a plot. Could you just say
sure.
what happens to the entanglement without maybe, oh, the plot's right here, okay.
I have to, or maybe yeah. So on the left, you see a plot of the, of the concurrence with the chemical potential and the Coulomb repulsion. And here you really see that as long as, actually this is not a good scale, it should be temperature here. Just imagine there is temperature. As long as the Coulomb repulsion is high and the chemical potential is high, while maintaining that this is higher than this, you have almost perfect entanglement. You don't have to actually go to infinity.
And are those realistic numbers, like U is 15 and
so
let's say mu is 6?
For this, we've checked with quantum dots. It's realistic for quantum dots. Okay. Actually, quantum dots are quite natural for this because there's well, electrons have natural Coulomb repulsion. You don't have to engineer.
Thank you.
Thanks. Okay, do you have any other question? It seems no. So let's thanks, Shishir once again for the nice talk. And we